In the Beginning by Dr. Walt Brown. A flip book is available at creationsciencecenter.org, page 216. Take a look at Liquifaction, Plumes and Mounds. Formation of liquefaction plumes and mounds. A. During the flood phase, global liquefaction sorted water-saturated sediments into nearly horizontal layers. B. During the compression event, massive liquefaction caused less dense sand water mixtures to float up as plumes through denser overlaying layers. See figure 64. Shows a similar phenomenon. Later, if surface layers were not cemented as well as the sandstone plume, the surface layers could erode away, leaving the harder, more resistant plume exposed. C. If a plume spilled out on the ground, a mound would form. Oh, Ayers Rock. Sure. Okay. Wow. See the man. That is huge. Figure 113, liquefaction plume. Plume. 1. 100 of these plumes are found in Kodachrome Basin State Reserve in south central Utah, 10 miles east of Bryce Canyon National Park. I am standing at the bottom left of this tall plume. Wow. Liquefaction plume 2. This plume can be traced down several hundred feet through the large rock in the bottom half of the picture. The plume rose from a specific horizontal sandstone layer that has identical chemical characteristics. After the plume pushed upward, cementing occurred, with the sandstone plume becoming harder than the material it penetrated. Softer layers surrounding the plume later eroded away, leaving the plume exposed. Notice the person waving at the bottom left of this plume. Wow. Okay, liquefaction plumes and mounds. The large water content of liquefied sand layers, 40%, would have made them quite buoyant. Whenever a low-density fluid layer, such as a water-sand mixture, underlies a denser liquefied layer, the lighter fluid, if shaken, will float up. Will float up in plumes through the denser fluid. Sand plumes that penetrated overlaying layers are seen in many places on Earth. Figures 112 and 114. Yep, that's what we see. Some plumes, especially those rising from thick, laterally extensive sand layers, spilled onto the Earth's surface. This spilling out resembled volcanic action, except water-saturated sand erupted, not lava. Small liquefaction mounds, as they will be called, appeared when liquefaction occurs during earthquakes. Hundreds of liquefaction mounds are found in basins, former post-flood lakes in southwestern United States. Why basins? During the compression event, liquefied water, sand mixtures in many places erupted up onto lake bottoms. Being surrounded and permeated by water, they would have quickly slumped into the shape of an upside-down bowl, a liquefaction mound. As the flood waters drained at the end of the flood, most liquefaction mounds were swept away because they did not have time to be cemented. However, mounds inside post-flood lakes basins were cemented as each lake cooled and its dissolved silica and calcium carbonate precipitated out of the solution. If a lake later breached and dumped its water, the larger cemented mound could resist the torrent of rushing water and retain their shapes. The basins that held Grand and Hopi Lakes, shown on page 224, contain hundreds of mounds, such as the one in figure 115. The sudden breaching of those lakes several centuries after the sudden breaching of those lakes several centuries after the flood carved the Grand Canyon. Figure 115. This is the one he's talking about. Liquefaction mound. This and hundreds of similar sandstone mounds occupy the basin of the former Grand Lake. The breaching of Grand Lake carved the Grand Canyon. The compression event produced massive liquefaction in water-saturated sand layers. During the few minutes the liquefaction lasted, some sand-water mixtures erupted, much like a volcano. Here, the eruption was onto the floor of Grand Lake. The large, mushy pile of sand quickly settled into the shape of an upside-down bowl. As the floodwaters drained off the continents, this large, wet sand pile was protected because it was deep in a lake. As the warm lake cooled, silica dissolved in the water was forced out of solution, thereby cementing the mound's sand grains. A century or so later, when Grand Lake spilled out, rushing water around the mound eroded the softer sediments on which the mound rested, producing the deep moat that separates the man in the lower right from the mound. Oh, wow. Fascinating. Liquefaction mounds have holes in their sides showing where internal water escaped. The channels have collapsed near the mound's surface where there was much less collapsing stress. Those holes now look like pock marks. Some have claimed they are erosion features from wind or rain. Obviously, wind and rain would smooth out pock marks, not make them. Besides, these pock marks, which will be called water vents, are found only in the sides of mounds, not the tops, where they should be if outside erosion formed them. For centuries after the flood, water drained out of the mountains and cliffs. Caves were carved by outward flowing water. New inhabitants to an area sought out and settled around these plentiful sources of water. Thus, many ancient cultures believed that water originated in mountains and flowed out of the caves. Years later, as water sources dwindled, communities were forced to leave. Prosperous cultures such as the Anasazi and cliff dwellers suddenly disappeared from an area, causing anthropologists to wonder if disease, war, famine, or drought destroyed those ancient communities. No, their water supply dried up. Ayers Rock. This popular tourist attraction in central Australia is 225 miles southwest of Alice Springs. Ayers Rock rises 1,140 feet from the desert floor and has a perimeter of 5.6 miles. Geologists who try to explain the origin of Ayers Rock say it is sand from the Musgrave Mountain Range 60 miles to the north and was dumped by water at its present spot. To account for its vertical layers, they say the rock tipped, but the force, energy, and mechanisms to do this were never explained. However, most geologists admit they do not know the origin of Ayers Rock. Ayers Rock has characteristics of both a broad liquefaction plume and a liquefaction mound. Its surface layers, bedding, are nearly vertical, and they connect to a horizontal sandstone layer underground. It formed in the Amadas Basin, whose contained waters covered and protected it while the floodwaters drained from the earth. Probably most soft sediments through which the plume arose were swept away when the basin's lake finally discharged. The many large holes in the sides of Ayers Rock show where water drained out. Almost 20 miles away, this same deep horizontal sandstone layer also connects to a series of liquefaction eruptions called the Olgas. The sand grains comprising Ayers Rock are jagged. If exposed to rapid currents, would have become rounded. Had the grains been weathered for thousands of years, they would have become clay. Instead, these grain characteristics are consistent with the gentle currents produced by liquefaction and the rapid cementing in years after the flood. That was Ayers Rock. Take a look at that again. Okay. Cross-bedded sandstone. Dry sand can have a maximum slope of only 32 degrees. Cross-bedded sandstones, such as shown here, often have greater slopes. Therefore, this sand was probably wet when the layers tipped. Notice the top and nearly horizontal layers obviously slid over and beveled the tops of the layers below. Something such as water was needed to be lubricating the sliding and otherwise horizontal layers would be wrinkled or crushed. But what was the lubricant and what was its source? What combined the lubricant between the sliding surfaces and what tipped the lower layers and what pushed the top horizontal layers over the tipped layers? Yeah. As the compression event began near the end of the flood, these sediments, all horizontally layered by liquefaction during the flood phase of the preceding months, were riding on decelerating hydroplates. The deceleration rapidly compressed the water-saturated sand, just as your hands might horizontally compress a wet sponge. Water squeezed out of the wet sand formed a temporary liquefaction lens that decoupled the sliding layers above from the layers below that were being simultaneously tipped by the horizontal compression. The compression event was over in minutes. Also notice the tip layers are slightly concave upward. Over long distances, this concave upward pattern is often seen throughout the world's sedimentary layers. Concave upward. Okay. It occurred because a layer pushed horizontally, even if lubricated, would collide with what is being pushed on into. However, the more the layer is tipped upward, the less the resistance and the greater the thickening. Thus, these compressed and sheared layers are concave upward, increasingly tipped upward along their length in the direction of their movement. The Appalachian Mountains are one of the most dramatic examples of this. Huh. Medium-sized water vents. Geology professor Dr. Douglas A. Block points out one of many holes in the side of a huge liquefaction mound in southern Utah. If these holes were places where rock was weakly cemented, similar holes should be on the tops of the mounds. Instead, the tops are smooth. Cementing in mounds and cross-bedded sandstone is remarkably uniform and hard, showing that the cement was uniformly dissolved throughout the water that saturated the sand. Water vents. These water vents are smaller than a pebble. Others, such as those in Ayers Rock, are larger than a car. Water vents are quite different from the shallow and smooth bowl-like depressions which wind and rain erosion produce. Ripples in the Continental Divide. Page 219. Ripples on the Continental Divide. These ripple marks obviously made by water flowing powerfully in the direction of my pencil are found at dozens of locations within 100 feet of the Continental Divide, along Hidden Lake Trail at Logan Pass in Glacial National Park, Montana. The Continental Divide is an imaginary line stretching from Alaska to the southern tip of South America. Along the crest of the Rocky Mountains, Andes mountain chains, falling rain to the west of the Continental Divide flows toward the Pacific Ocean. Rain falling to the east of the line eventually enters the Atlantic Ocean. Below these rippled sandstone rocks are 7,000 feet of layered and cemented sedimentary rock whose sediments were deposited through water. What sequence of events produced all this? First, sedimentary deposits, 7,000 feet thick, fell on a seafloor over hundreds of square miles. Then, liquefaction sorted the sediments into thin, flat layers rapidly because irregularities are only on top. Next, water had to flow powerfully over the uppermost layer to produce non-symmetrical ripple marks in wet sand, but ripple marks are easily erased just as sandcastles on a beach are destroyed in a few days. Therefore, a thick layer of mud had to rapidly blanket and protect the ripple marks. Finally, something pushed the seafloor up to form the Rockies and Andes Mountains, a task requiring gigantic forces and energy. Notice that plate tectonics provides neither. Besides, the kinetic energy of a plate moving at only about an inch per year is so trivial that it could never push up a mountain. Later, the sediments were cemented by chemical agents that were spread uniformly throughout the billions of cubic miles of loose sediments. Finally, erosion and weathering removed the blanket, exposing the cemented sandstone ripples. Did these ripples form at their present elevation, about 7,100 feet above sea level? No. Earth does not have enough water to rise uniformly to that elevation. Even if that was at one time that much water, where did it all go? And what could lift such thick layers of sediments that high? Could ripples form in high lakes and become cemented? We don't see that happening today, nor are the necessary chemicals present. Were the Rocky Mountains lifted slowly over millions of years? The energy, forces, and mechanisms for doing so have never been explained. But if the Rockies somehow rose slowly, as plate tectonics claims, its peaks would experience the greatest erosion and weathering. Based on today's conditions and measurements, the mountain and its cemented ripple marks would erode faster than the mountain rose, so we would not see any ripple marks. The hydroplate theory, however, supported by hundreds of other evidences, easily explains ripples on the continental divide. Sediments eroding by the escaping subterranean waters during the flood were quickly deposited through those waters. Sediments eroded by the escaping subterranean waters during the flood were quickly deposited throughout those waters. On the continents, those deposits averaged more than a mile in thickness. Liquefaction sorted most of them into the prominent layers we see today, and fluttering hydroplates produced gigantic waves, causing ripples even on the deep seafloor. The compression event buckled, crushed, and lifted the Rocky Mountains within an hour. That lifting of the seafloor up through the water also caused a powerful ripple-producing flow. Before the flood, supercritical water in the subterranean chambers dissolved and uniformly spread cementing agents such as silica and calcium carbonate through the water. Months and years after the flood, the warm flood waters cooled, so those minerals came out of solution, lodged as precipitated solids or cement in the tiniest spaces between sedimentary grains. What were the forces, energy, and mechanism that produced ripples on the continental divide? Gravity, the kinetic energy of massive hydroplates sliding downhill, and buckling. See also seashells on mountaintops on page 56 and a whale of a tail on page 147 and figure 52 on page 127. Let's see page 52. Buckled mountains, of course. Buckled mountains. Yes, indeed. Buckled mountains. Textbooks and museums frequently refer to some uplifting force that formed mountains. Can you see that an uplifting force by itself would not produce this pattern? Horizontal compression was needed to buckle these sedimentary layers near the Sullivan River in southern British Columbia, Canada. Such layers, seen worldwide, must have been soft like wet sand at the time of compression. Today's surface rocks are brittle and cannot bend. In the Beginning by Dr. Walt Brown. Flipbook available at creationsciencecenter.org.